Welcome back to ECE 3030. Today we are going to continue our discussions on the CMOS inverter. So in the last lecture, we talked about the basic concepts of the CMOS inverter. So if you want to implement the logic function like inverter into the silicon, then the simplest way to do that is to use one NMOS and one PMOS transistor connected in this fashion. So we talk about the cross-sectional view of the CMOS inverter. So basically you can fabricate the NMOS and PMOS on the same substrate, on the same silicon wafer, and make the connections like this. So this will be the CMOS inverter. And also from the top view layout point of view, you can have one-to-one mapping from the circuit schematic to the geometry like dimensions in the layout. So today we are going to continue our discussions on the operations of the CMOS inverter. And the first one is we want to talk about this voltage transfer curve. This is a very important concept in the CMOS inverter. So basically we are looking at the CMOS inverter and the input and output voltage. We say Vi and Vo. So this voltage transfer curve, VTC, basically talk about the relationship between the input and output voltage. So the x-axis is the Vi, y-axis is the Vo. So as we sweep the Vi from 0 to VDD, the power supply, then the output voltage Vo will change from the VDD to ground eventually. And this is the transition between the high voltage to the low voltage. And from this VTC curve, we can have a few definitions. First one is this VIL. So IL is short for input low. So this is the voltage we defined here. That is, we take the slope of this VTC curve to be -1. So basically, if you draw a line with like this kind of 135 degree, then it will be the slope -1. So here, this voltage is defined as the VIL. So the input voltage, if it's within this range, we think the input voltage is logically low, like logic 0. This is because if input is in this range, the output from this VTC curve, you see that the output is pretty close to the VDD. So the output voltage is high. Similarly, we can define the input high, the VIH, that is here, with the same slope, -1. So we can have the VIH. So the range between the VIH and the VDD, we can think this is a logic input 1, and here is logic input 0. Here the logic input 1, if the voltage is in this range for the inputs, then the output voltage is very close to the ground. So the output voltage is from here to basically to ground. So the output voltage is pretty low. If we look at the voltage scale, This is what we just discussed. So this is a input voltage range. So input logic 0 can be from 0 voltage to this VIL, that is here. Because in this range, if you draw the output will be pretty much close to the VDD. So let's say this is output. And you know the inverter is going to invert the signal. So the output will be in this range. So here, in this range. So we reflect with this range here. And if the input is logical 1, it can be within this range because the output will be pretty close to the ground. Or in other words, we can tolerate some noise in the input voltage. So if you think about the input voltage has some noise, ideally should be 0. But if it has some noise, as long as the noise is within this range, within this range, the output is more like 1. So here we define the noise margin, like the noise margin low, NML, is from this VIL minus the VOL, which in this case is 0. So basically it's in this range. And similarly, we can define the noise margin high, which is from this VIH to the VDD. So that is noise margin high. So in this particular case, this is the same as the VIL, and this is VDD minus this VIH. That is the noise margin high. Or in other words, the inverter has a good attribute, that is to suppress the noise in the circuit. For example, if you think about the inverter, input maybe is logic 1, but it may have some fluctuation due to the noise. That is a fluctuation in this range. But after the inverter, then the noise is suppressed into this small range. So the logic output 0 will have much smaller noise. So this is a very good property for the digital circuit in general. That's why digital circuit is digital circuit has the integrity of the signal because it can somehow tolerate the noise. Of course, the noise needs to be within this range. If the noise is too large, you see the output will flip to the wrong value. If the input is larger than this range, then the output will no longer be the ideal output. Then it will be somewhere here. Then logically, it will be undefined. So any questions on this slide? Okay, so here we basically define the noise margin. And we have two important voltage levels, that is VIL and VIH, which is defined as the slope becomes -1 in this VTC. And next, let's look at the ideal CMOS inverter. So here ideal means we are going to assume the square law IV. That is the first order IV model as we discussed in the lecture 11. So we ignore the channel length modulation effect, and we also ignore the sub-threshold current. Then this is like the very simple first order square law IV. So if we use this assumption, then we can redraw the VTC, and then the VTC will look like something shown here. So the transition will be very sharp if we assume this ideal square law IV. So the transition here is very sharp. And also, here we will assume this is a matched inverter. So match means the CMOS has the same like NMOS and PMOS strengths. They are matched. So if they are matched, then this is symmetric towards the center, or actually say it's mirrored towards the center. So this is the ideal CMOS inverter with this matched condition, and we will go back to this point later. But from this VTC, we can discuss the operation regimes as we change the input voltage from 0 to VDD. So those transistors will go through different operation regimes sequentially as we increase the voltage from 0 to VDD for the input. So firstly, if the input is 0, here, you know this is the gate, this is source for the NMOS, and this is the source for the PMOS, this is the drain. So if the input is 0, this VGS is 0 for NMOS, then NMOS is off because it's smaller than the threshold. So if NMOS is off, Qn is off initially, and then the first order model ignores the subthreshold current. So then this is like open circuit, current is 0. Then the output voltage will be the same potential as the VDD because there's no current in this branch. If NMOS is off, no current, then the PMOS, that means source and drain will be equal potential. Then the output will be VDD, the power supply. Until here, the point A, where the input voltage is the same as the threshold voltage of the NMOS. Now at this moment, the NMOS is going to be turned on, and after that, then we will have the current flow. So once we have the current flow, then you know the source and the drain will be no longer equal potential for the PMOS. So that means the drain will be lower potential for the PMOS. The output will start decreasing from the VDD. So that's why you see here the output is going to decrease. So in this segment from A to B, then you will see that initially the VGS for the NMOS is kind of small, just above the threshold. But the VDS for the NMOS, because the drain is close to the VDD, so it's a large voltage. So you will see that NMOS Qn is in the saturation from A to B. And similarly, you can look at PMOS. PMOS, as we discussed, the VGS is here. We need to take the absolute values for the PMOS. So the input voltage is kind of low at this moment. So the VGS is large because the difference here, if Vi is small, then the difference here will be large. And then for the PMOS, the VDS for the PMOS will be small because the VD just decrease from the VDD. So it's still close to VDD. So this difference is very small. So for the PMOS, you will conclude that PMOS is in the triode region from A to B. And then you can continue this analysis from B to C. Both Q and QP will be in the saturation at this moment. Then the input voltage is kind of high, and then this output voltage is in the middle. So both NMOS and PMOS are fully turned on. So those are in saturation. And after that, then the situation will be just the opposite. Because here, as we discussed, everything will be symmetric or mirrored according according to the center point. So after that, as we further increase the input voltage, then the Qn NMOS will be in the triode and PMOS will be in the saturation. And eventually, when the Vi is large enough, then the PMOS will be off. So this is the whole switching curve. If we want to analyze the operation regimes in this VTC according to those segments. Okay, then next we will talk more about the matched condition. So we briefly mentioned that for the matched condition, we want NMOS and PMOS look the same. So that means here this middle point will be half VDD, half the supply. And this middle point we give the name Vm. This is defined as when the input voltage equals to the output voltage. And we call this is the Vm point. Or in this plot, if you draw a straight line with 45 degrees, then you know this is like y equals to x. That means Vo equals to Vi, this straight line. So the intersection here will be the Vm voltage. And for the matched case, Vm will be exactly half VDD. And then this curve will be mirrored respect to this Vm point. So to make this match, we have to make sure they are mirrored. So for example, here this segment A and the segment D to the VDD, they should be the same. So segment A and segment D, so this point and this point basically are determined by the threshold voltage of the NMOS and PMOS. So the first criterion is the threshold voltage for the NMOS and PMOS should be the same. Of course, for the PMOS, we take the absolute value. So we have this first criterion here. And secondly, the current should be the same in this Vm points. So both NMOS and PMOS are in the saturation. And that means the coefficient in front of the voltage terms in the current equation should be the same. So this is like the current, you know, is mu n COX W over L n. And then you have the voltage term VGS minus VT squared. And in the Vm points, this will be Vm. And it will be half VDD. So this is NMOS current. And the PMOS current, IDN and IDP, will be mu P COX W over LP. And the VGS, because this is in the middle point, so it will be VGS still minus VTP. And this is absolute value. So this one will be VDD minus half Vm, because it's in the middle, so this is also half VDD. So you want to make sure those currents are the same, because they are in the same branch. So you can conclude that the coefficient here needs to be the same. That is the criterion here. COX is the same for the same technology node. Then the COX is always the same. COX the same. So then you will have this condition. And also for the same technology node, same tech, the COX the same, and also the L is the same. For the same technology node, for example, if it's Intel's 14 nanometer, then your L is the same as the NMOS and PMOS on the same technology node. So then what is left is this WP and WN and mu n and mu p. So here you see that the mu n and mu p is the mobility ratio, and we know in the silicon mu n is larger than mu p. So basically electrons moves faster than the holes. That will be translated as the Wp larger than Wn, because this is inversely proportional. Wp over Wn is mu n over mu p. Or in other words, if you want to make the CMOS inverter matched, then you have to make sure the PMOS transistor is larger than the NMOS transistor in terms of the transistor width, W. So this is generally true for the digital circuit. Usually the PMOS needs to be wider than the NMOS if you want to make the matched condition. So why do we care about the matched condition? Because in the matched condition, the circuit will be symmetric in terms of those metrics. For example, if you think about the matched condition for the noise margin, then the noise margin low and noise margin high will be exactly the same, right? Because they are respect to the Vm points. And if Vm is half VDD, then this noise margin low and this noise margin high will be the same. And later, when we talk about the lecture 13, you will see that if the CMOS inverters matched, then the delay will be the same as well. So what delay? So you have the delay from 1 to 0 transition and 0 to 1 transition. So the speed will be the same. When you do the computation and logic function, you have the 1 to 0 transition, 0 to 1 transition. So those two will be the same, no matter the input is high to low or low to high, if the CMOS is matched. So that's why we want to achieve this matched condition for the practical reasons. So any questions here? This is on the matched condition. And again, so we have those two criteria here. Threshold voltage is the same, and this coefficient in front of the voltage terms in the current equation should be the same. And that is often translated to this ratio of the width W, P over Wn, like mu n over mu p. Alright, then let's derive the VIH. So what is VIH? VIH is this number here. So that is defined the input voltage high. So we want to calculate what is VIH. And again, in this segment from C to D, here the PMOS is in the saturation, NMOS is in the triode. So we need to use this condition to derive the VIH. And we do it for the matched CMOS and assume the square law IV. So those are two assumptions. We are going to have here square IV and also the matched condition. So the matched condition basically tells you that the Vt n equals to the absolute value of Vtp. Threshold voltage are the same, and the coefficients Kn and Kp in the current equation are the same. So here the NMOS is in the triode, PMOS in the saturation in that VIH. So we can use the equation to, let's say, the current equations to establish this formula here. So no matter what, the NMOS and PMOS current will be the same because they are in the same branch. Current will be continuous. So this IDN will be the same as IDP. So what is IDN? That is the current for the NMOS, and now NMOS is in the triode, so we have to use a triode equation for the NMOS. And if you recall, the triode equation basically is the Kn and the VGS minus VT, VDS, and the minus half VDS squared. So that is the triode equation. And then what is the VGS for the NMOS? So GS. So VGS, you see here is the same as the VI. So here we have the VI here. And then what is the VDS for the NMOS? VDS is the output voltage, VO. So that's why we here substitute the VDS with the VO. So this is on the left hand side. On the right hand side is for the PMOS currents. The PMOS is in the saturation in this case, and the IDP will be half Kn and the VGS minus VTP squared. So then what is the VGS for the PMOS? G is here, S is here. So VGS, you see, is the difference between the VDD and the input. So that's why we have this VDD minus VI as the VGS. And then we have the threshold voltage because we assume it's matched. So it's the same as NMOS. So we just use VT here, the same as NMOS. And then here Kn and Kp are the same. Sorry, this should be Kp. So then we have this equation. Kn and Kp cancelled. So we have this one. Only the voltage matters here because IDN is always the same as IDP. And then the next, we will have some tedious derivations. I don't require that. But we will quickly go through the derivation here. What is important is this the approach. So basically, you first determine the transistor's operation region. Second, you use the current NMOS and PMOS the same to establish this equation. Okay, so the rest is to differentiate both sides relative to the VI. So this equation, we take the derivative of VO respect to the VI. So you have this dVO over dVi. And then we can do it for the left hand side. So you will have this one. And then VO, because it's the second order, after you take the derivative, then you have to rewrite it to be like this. This is like your calculus. And then on the right hand side, then it's VI itself. So then still the second order will become first order. So you have this equation. And then we are going to substitute at the VIH point. So the VI will be this VIH. This is what we want to solve for. And at this VIH point, we have the criterion that our condition that this will be a -1, the slope. So what is the slope? This is a slope. VO respect to the VI. So this derivative is the slope. So this becomes -1. So basically we plug in the -1 here and -1 here. Then we can solve for the VI. We can solve for the VO. So I will skip the details. So after you do that, then you get this one. The output voltage is VIH and minus half VDD. And then you need to substitute this back to the original equation here. This one, you need to substitute back to here. And then solve for the VIH. Eventually you will get the VIH like this one, as we have here at the bottom. So we will skip the derivations. It's very tedious, and we will not require the derivation in this class. So what you need to know is this final conclusion. If you have the matched condition and assume the square law IV, then the VIH can be analytically represented by this one. So it only depends on the power supply VDD and the threshold voltage. So we can apply the same approach to get the VIL. So what we have on the earlier slide is this VIH, and we can also get the VIL, which is this one. But you know those two are mirrored respect to the half VDD in this matched condition. So you can expect this VIH and VIL. One is above the half VDD by this distance, and the one is below the half VDD by the same distance. So you can get those two. This is VIH and VIL in this matched condition. And again, for the noise margin high and noise margin low. So noise margin high is this range. This is noise margin high, and this is noise margin low. So you will use the VDD to minus the VIH. So you will get a noise margin high. Then after you do that, then you get this one. And noise margin low is just the same as VIL because it's minus 0. So it's the same. And you notice that the noise margin high and noise margin low in this case are the same. This is because this is a matched condition. So this is as expected. Any questions?